Okay, so welcome to the next video in our flip series. We're going to be talking about today areas of special quadrilaterals. So in our last video we talked about areas of regular quadrilaterals like squares and rectangles, and we also spoke about triangles as well. This one is about special quadrilaterals. So remember from our last key idea here, an area is two lengths that are multiplied together. So remember that we get one length going this way and another length going this way, and if we multiply them together we get ourselves an, if I can spell it correctly, we get ourselves an area. Okay, right, so we need to be looking at, when we're doing these special quadrilaterals, we'll always be creating two lengths we multiply together to get our area. Right, so first off we have a parallelogram. So when we're looking at this one here, okay, parallelogram, so we have two parallel sides. So we got this one here is parallel to this side here, and this side here is parallel to this side here. Okay, the arrows sort of indicate parallel lines, and these double dashes, they're the same length. Dash here, same length. Okay, there's a lot of things that we'll see about the parallelograms. There's with the interior angles, there's some similarities there too. Right, so when we're talking about working out an area for this thing though, actually parallelograms are really easy. So if we grab, I'm not going to mark in red here, so if I get this triangle here and create a perpendicular length here, okay, and we call this a height, okay, and if I get this triangle here and I move it over to this side and sort of chuck it right here, what have I made for myself? This part here, I just put in a different color, I've created a rectangle, okay? And so our area of a rectangle is, just remember, length times width. So for a parallelogram, all we're going to do is that it will be the base length, which is this one here, times this perpendicular height one here. Okay, so I know this drawing's got a little bit messy now, but I just wanted to see that we get this triangle, move it over the other side. So the area of a parallelogram, remember that I like to see the little subscript of the shape you're trying to work out. So this is base times perpendicular height. Okay, right, and if I made this one say 6 meters and this perpendicular height was, I don't know, 4 meters, we would just simply have 6 meters times 4 meters equals 24 meters squared. Okay, so working out areas of parallelograms, pretty easy to do. Okay, moving on to the good old rhombus. Okay, so these are sort of like a squashed square, in that again we got parallel lines here, parallel lines here as well. So the biggest difference we have besides to the parallelogram is that by the single dashes here you can see that they're all exactly the same length. Okay, now obviously we can move this triangle here and create the same kind of thing as a parallelogram, but there's also other measurements we can take with the rhombus. So if I grab my red here and sort of sketch out these lengths here, okay, and kind of create put the rhombus sort of inside a rectangle, okay, and you can sort of see here that this triangle and this triangle are the same, this triangle and this triangle are the same, this triangle, this triangle same, this triangle and this triangle are the same. So what we end up having is that the area of a rhombus is half of the rectangle it fits inside. Okay, Okay, so it's kind of a basic way of talking about it. So essentially, if we grab this length here, okay, now a lot of textbooks kind of just call this length here sort of just an X, and this length here sort of a Y. Okay, so that's an X up there. So essentially, the area of this rhombus is equal to the sort of the diagonals. Okay, so really we got diagonal 1 times diagonal 2, and I've just called them X, and times Y. And if I made this, I don't know, 7 meters and 6 meters, I'm going to have 6 meters times 7 meters is equal to 42 meters squared. Okay, so nothing too exciting about the rhombus, just sort of remember that it's half of the rectangle that it fits inside. Okay, so you just multiply these diagonals here. All right. Okay, moving on to the kite. You know, not a very interesting name. Obviously, it just comes from the fact that it kind of looks like a kite, and that's sort of it. Oh, let me move my screen around. It's just mucking up a bit there. All right. So, essentially similar to our rhombus, and some of you might kind of notice this, that if we get draw ourselves rectangle terribly sort of around it. Okay, again you can see that the kite, so these triangles are the same, these triangles here the same, these ones here the same, these ones here the same, and so we end up with the idea that a kite area is half of a rectangle made out of its diagonals. Okay, so if we were to make this length here, like again an X, and this length here a Y length, therefore we'll have the area of our little kite here is equal to the X, whoa, half of, I just realized I made a big error on my rhombus. I'll just rewind up to that in a sec. So half of the X times the Y. Okay, and let me just scroll up to our rhombus. This is half of the X times Y, half of this, half of 42 meters squared, which is 21 meters squared. That was a bit naughty. Right, so half of it. Same here. If I had this as 8 and 4 meters, therefore this is equal to half 4 times 8, which is half of 32, which is equal to 16 meters squared. Okay, so remember this kite and the rhombus are half of the diagonals multiplied. Okay, trapezium. So this is a bit of a weird one. Best way to sort of describe how we approach this one is we're looking for a couple of different measurements. So we have a perpendicular height here, and we're not doing any switching around of triangles or anything with this one, but you sort of think that if we leave the height the same, we kind of bring this corner in to here, which kind of pushes this part out a bit. And you can kind of see that we sort of can make a rectangle out of this thing. Okay, right, so what we end up doing is we find the average of, let's call this length A, and this length here we're going to call B, and what we end up doing is we find the average of these two, okay, and multiply it by this perpendicular height. Okay, so what that ends up being is that the area of our trapezium is equal to the average of the side of the top and bottom. So average of top and bottom times the perpendicular height. Okay, and so that ends up being, so remember averages of two things, you add them both up, divide by 2, so it's half of a plus b times the perpendicular height. And so let's just give these some numbers, I don't know, 3, 7, so let's go centimeters this time, centimeters, and I'm going to make this one here to be 3 centimeters. Okay, so let's go. Area of the top and bottom of this trapezium is the average of top and bottom times perpendicular height. So half of 3 plus 7 times 3. Okay, so we work out our brackets first. Half of 10 times 3. So we have 5 times 3 equals 15 centimeters squared. Okay, so just to quickly scroll back up and down and recap those, we've got parallelogram is the base times the perpendicular height. Okay, the rhombus is half of the diagonals multiplied. Kite, again, height, half of the diagonals multiplied. Trapezium, we find the average of the top and the bottom and multiply it by perpendicular height. Okay, so that's our 4 special quadrilaterals we're looking at this term. Essentially just memorize those formulas. They're sort of pretty intuitive as to how they come about. So my suggestion would be is just to do a bunch of examples and we'll be having a look at some of this stuff in class. So